So guys, when we are dealing with various kind of velocities, like as I already told you, there is a RMS velocity, and just now we discussed about Maxwell distribution and we have seen the most probable velocity. And obviously if the molecules have a different velocity, there must be average velocity also. So how can we define those velocities? So first of all we will talk about average velocity. So average velocity, in a simple way, there are different velocities possessed by a molecule. So let us consider there are n1 number of molecules which have a velocity of u1, n2 number of molecules which having a velocity of u2, and so on. So u3 ... and u4 and so on. So average velocity u average is equal to n1 u1 plus n2 u2 plus n3 u3 plus and divided by total number of molecules. Okay, so that is the average velocity. So this is actually the theoretical definition. But if you have to calculate the average velocity, there are various relations. Directly we will write a formula, that is square root of 8 RT upon pi m, or square root of 8 PV upon pi m, and this is for the 1 mole of a gas. So this m stand for molar mass of the gas. So this is average velocity. Then root mean square velocity, RMS velocity, C bar, or sometime people are also called as the URMS. It's not the same thing. So what do you mean by root mean square velocity? We will be using the same concept. Only the thing is that what we are doing, we are taking square, u square is equal to what? n1 square u1 square plus n2 square u2 square plus n3 square u3 square and so on, divided by n1 plus n2 plus n3 plus and so on. So if you take square root, so that u is equal to square root of all this part, n1 square u1 square plus n2 square plus u2 square and so on, divided by n1 plus n2 plus n3, and we just now we have derived this as what? Square root of 3RT upon m. And most probable velocity that is MPV. So the velocity possessed by many number of molecules in a container called as most probable velocity, and that is given by UMPV is equal to square root of 2RT upon m or square root of 2PV upon m. Okay. Now if I consider at 298 Kelvin, I will be getting a particular value. Okay. So we can get the relation between average velocity and RMS velocity and most probable velocity. No need of remembering those values, because those values actually in many books it has calculated. In problems you can directly take the ratios and you can calculate that relations. So there is no need of remembering those values. Okay, values actually calculated by using these relations. What we need to remember? These relations, because those relations we are going to use while solving problem, the conceptual problems. Okay. So these are some of the problems which are based on this concept and the kinetic theory of gases. The problems are simple and straightforward, but remember that, as I was telling you, that we need to use our concept. So first problem, at 400 Kelvin, the RMS velocity, C bar means RMS velocity of a gas X which has a molar mass 40 is equal to most probable velocity of a gas Y at 60 Kelvin. Find the molar mass of Y. So we need to solve this problem. This is quite simple problem. What they are saying, RMS velocity C bar of X is equal to most probable velocity MPV of Y. Okay, but what is RMS velocity? We know this RMS velocity is equal to square root of 3RT upon M. M is what? 40 is equal to square root of, so this is T1 I am considering because temperature is 400 Kelvin, and here square root of 2RT RT2 upon My. So that we need to calculate. So after squaring we can say that 3 into 400 divided by 40 is equal to 2 into 60 divided by My. Therefore, My is equal to, this becomes 10, 30, so 2 into 60 divided by 30, so that becomes 4. So molar mass of that gas is what? 4. Okay, so it must be helium gas, right? So this is answer for example 1. Now example 2. RMS velocity of hydrogen is root 7 times the RMS velocity of nitrogen. RMS velocity of hydrogen is root 7 times the RMS velocity of nitrogen. So, to solve this problem, we will read that. If T is the temperature of the gas, then which of the following is the correct relation? So, what we are saying? Hydrogen is equal to root 7 times to that of a CRMS of nitrogen. What is the relation? We know that square root of 3RT upon 2 hydrogen is equal to, so this is for T hydrogen, root 7 times into square root of 3RT of nitrogen divided by 28. If we square this, so what we can say that TH2 is equal to 14 into TN2 divided by 28, which means we can say that 2T hydrogen is equal to T of nitrogen. Okay, so here 3 and 3, R and R get cancelled, so this becomes 2, so that goes here, so 14, right, and if you simplify it you will get this way. So what we can say that temperature of nitrogen is greater than temperature of hydrogen. Okay, so what will be the option? C option will be the correct option. Okay. Now we'll go for the next question and we'll read that. According to kinetic theory of gases, which of the following are the correct statements? Heavier molecules transfer more momentum to the walls of the container. Heavier molecules transfer more momentum to the walls of the container. So, momentum, mass into velocity. So, if the mass is more, definitely the momentum will be more. So, A is correct. Between collisions, the molecules move in a straight line with a constant velocity. Now, this is very important concept. When I am talking about this molecule and the second molecule is at this position. Now, when this molecule is moving in this direction and when this molecule is moving in this direction, before they are coming at this point, they are moving in a straight line. Once they come here and they collide, they will change their direction. Again they start moving in a straight line. So before collision, the molecule never move in this direction. They always move in a straight line direction. Straight line direction. So B is also correct. Next one. Only small number of molecules have very high velocity. Recall the Maxwell distribution, where we plotted a graph. If you have seen, at any temperature, high velocity is actually possessed by very small number of molecules. So that is also correct. Collisions are always elastic, we know that. Before collision and after collision, there is no loss of energy. Therefore, that collision is called as a perfectly elastic collision. So all the four options are correct. So these two options actually we know, they were given in a statement also. These two options we have to apply your logic from the KTG, and actually they are also considered as the assumptions of KTG. Okay. So this is all about KTG, and actually this is all about your ideal gases. So as we know, ideal gases are those gases which obey all the gas laws, which obey the ideal gas equation PV is equal to nRT, which obey all the assumptions of kinetic theory of gases. But is it true for hydrogen, nitrogen, carbon dioxide, water vapors, sulfur dioxide, these many gases? And it was observed that those gases are not behaving or not obeying all those laws at different temperature, different pressure and different volume. Therefore, those gases are called as real gases, not ideal, therefore called as real gases. So how to give a relation between pressure, volume and temperature, and why those gases are not behave as an ideal gas, that also we have to consider. Various scientists has given various approaches to explain the behavior of real gases. The most accepted explanation was given by van der Waal, and that explanation actually tells a relation between pressure, volume, temperature at a wide range. Again, there are certain limitations for that van der Waal equation also, but van der Waal suggested some corrections, and those corrections are because of the invalidation of some assumptions. So all that things we have to discuss. One more thing is that whenever we are talking about gases, gases are compressible. But when we start applying pressure and if start decreasing temperature, what will happen? The molecules start coming close to each other. At one point of a time, those molecules, gas molecules or the gaseous state no longer become gaseous. It is converted into liquid state. And that plays a very important role in the liquefaction of gases. So liquid nitrogen, dry ice, like that. So all those parameters, all those physical state, the change in a physical state plays a very important role. And ideal gases never undergo liquefaction or solidification. Now why that is happening, that also we have to discuss. And that we will discuss in the next session. Thank you.